He will malform.
Ron, thank you very much. This is it's a great pleasure. It's a great honor. I am humbled, actually, to address this very distinguished audience. Speaking in this particular lecture room brings memories, I have to say. It's a very soft spot as far as I'm concerned. You will notice that I don't have a laser pointer. I have this. Many years ago, actually 16 years ago, 17 years ago, this department used to operate, I'm sure it does the same thing now, a peer observation system. So young lecturers were observed while teaching by more senior members of staff, just to provide some feedback, some ideas. I was very lucky at that point to be observed by Professor Paul Buckley, who definitely doesn't remember, but he was here. He was lurking somewhere at the back. He wasn't devastatingly critical as far as my lecturing style, but he did offer me a great piece of advice. Don't use a lecture pointer, he said. Use this, because if you want to point at something, you can generate some noise, and this wakes up people at the back rows. So I've never never looked back after this, I have to say. Usually, talks like that have to open with a bit of introduction regarding who the speaker is or where they come from. But I'm trying to making these talks interesting, so this excludes me as a theme for discussion. I will say something, however, regarding this chap whose named chair I am very honored to hold, Alexander Kennedy. Alexander Kennedy was made professor at UCL at a very young age, 26 or something, second half of the 18th century, whereabouts. He was a polymath, a Renaissance man. He was what we would call today an electromechanical engineer. Amongst his many accomplishments, he was instrumental in the electrification of London. At that point, he was he was actually the first European, as far as we know, that rediscovered the ancient site of Petra in Jordan and took pictures and brought those pictures back to the West. Thus, he became a fellow of the Royal Geographical Society. However, he's great. He was president of the IMechE, or the Institution of Mechanical Engineers, our institution. However, his greatest accomplishment, something that actually puts him in a very special place in my book, was that, again, at a very young age, he went to the university and asked for money, as we do, to set up a laboratory for the engineering students doing hands-on work. And this was a world first back then. Up until that point, engineers were doing their beam theory analysis on a piece of paper, and that was it. He thought that it might be good to get the students, to get them to get their hands dirty. And as I said, engineering laboratories are, you know, a must nowadays. There is no engineering department anywhere in the world that doesn't do that. He was first. So that's an interesting contribution in engineering education. I will structure this talk around three main themes, three main sections, let's say. I will say a few things about what fusion is, you know, the general introductory bit of any talk like this. Then I will tell you a bit about the research that started in this department, how it evolved commercially, where it is now, where it's going. And I will close with my view, a very subjective view regarding how this type of work and this type of energy can find its place in the wider society, if it has a role and what that role is. So apart from this work, I also do a lot of medical work, I have to say. And in medical conferences, I actually go to more medical conferences than I do to engineering conferences these days. This kind of slide is a must. You have to put a slide at the very beginning with your disclaimers, saying where you come from effectively. So there are disclaimers here. There are things that I need to declare. There is a commercial interest behind this company, First Light Fusion. There are things that I cannot tell you. There are things that I will not tell you even if you ask me. that have to do with trade secrets, patents that are being drafted, sensitive papers. Also, this is a simplified presentation. I know that I'm not addressing an audience of Nobel Prize physicists, so I have tried to make everything relatively straightforward, as straightforward as it gets. I have no equations. There are simplifications in what I'm going to say, so I hope this doesn't freak you out. So something that I think I need to say a couple of things. As human beings, as biological entities, we are restricted regarding our perceptive capability by the organs of perception, sensory organs, eyes, etc., but also the nervous system per se, the speed at which it can operate. If we want to see very big, we need telescopes. If we want to see very small, we need microscopes. If we want to see processes that are very, very slow, we need special types of photography, like time-lapse photography. You stand in front of your lawn, you're not going to get much excitement. If you have processes that are very fast, you need high-speed cameras. You need other types of equipment. So I think that this is important. It's important to emphasize that many of the huge expenditure programs in science and engineering are nothing but ways to expand our perception. Think of the Large Hadron Collider. Think of all the amazing telescopes that we've sent to space, etc. Very expensive, billion-of-pound projects. They all have to do with, seeing better, seeing faster, seeing wider. So what I'm going to do is I'm going to attempt an experiment. It works like 50% of the time. So if it doesn't work, please forgive me. It is perfectly safe. What can possibly go wrong, right? It involves a mallet. So this is just a typical glass that you get from the supermarket, a bottle. It had elderflower, I think, something like that. Nothing much will happen. They make these very sturdy because, they get a bit of rough treatment, so they wouldn't break just like that. This is regular tap water. It has a sign that says, no, don't drink, and the gents over there, so I won't try to prove that it's just water, but take my word for it. There's nothing explosive here. That's not necessary to be completely full. So I'm going to try something now. As I said, 50%. So I'm going to hit it a few times, not full force, so to speak. There is a sound cue there. So you may notice that there is an extra sound that shouldn't be there, okay? So that was fun and wet. But if someone tells me now that they saw what really happened, I'll argue that you're lying. Fortunately, we have good friends. This is Tad Truscott from the Splash Lab at Utah State University, who actually did point a high-speed camera on my bottle, effectively. And this is what he saw. He saw that when it gets hit, you get this array of small bubbles there. So let's look at that here. That they expand and collapse. Okay? So I didn't pick this experiment. Randomly, bubbles play a role into this discussion. Basically, what happens is that the glass wants to go down, but the water doesn't know that it wants to go down. Isaac Newton has instructed the water, stay put. So you create this gap over there, and void doesn't play well with nature. So when this collapses back, it creates a very dramatic, a very drastic effect. Bubbles have fascinated people. Even Leonardo da Vinci came up with this idea of the bubbles rising in a spiral fashion. So it's a topic. It has been a topic in fluid mechanics for a long, long time. This is my busiest and most charged slide. After this, it's fair sailing. What I want, basically four salient points that I want to emphasize. In the macroscopic world, the world we live in, we understand temperature. In the microscopic world of atoms and molecules and nuclei, etc., temperature means speed, the incoherent velocity of molecules jumping around. Okay? If I warm something up, the molecules basically go faster. That's number one. Number two, nuclei, the core where all the mass of atoms are usually always actually two types of particles, a neutron and a proton. Neutron is neutral, no charge, proton is positively charged, which means that nuclei don't want to get close together because the protons in them repel themselves electrostatically. There is a lot of force that's pushing them apart. However, if you have a way to bring those nuclei very close together and they fuse like they do in this example, where I have an isotope of hydrogen that's called deuterium, from the Greek word that means second, and another isotope that's called tritium, from the Greek word that means third. If these two isotopes actually merge, they produce a helium nucleus and a very fast-moving, very highly energetic neutron. Now, in order for this to happen, three things must actually take place. The first one is that they must move fast enough to overcome this repulsion, this electrostatic repulsion. As we have agreed, move fast enough means high temperature. The second thing that must happen is that they must meet. Actually, they must find each other, because if I have a very fast nucleus at that corner of the room and another one down there, they might be going as fast as you want. They will never collide. They will never create a fusion event. So this means that they must be close together, which means a lot of them, which means high density. And the third bit, which is slightly more esoteric, but it's an important concept, they have to, in order for this to happen, they have to stay in that vicinity for an adequately long time. And this is a term that's usually called confinement. So when these three, confinement time, high temperature, high density, happens, you can get fusion events. And a typical fusion event is shown here, where you have, as I said, those two isotopes merging, fusing, and producing these products. Now, the purest physicists amongst this audience is going already ballistic. They are saying, this is an oversimplification. Where is Lawson's formal definition? Where is quantum tunneling? Where is the ionization? Where are the equations of state? It's not this kind of talk, okay? It's a simplified talk, so please bear with me. Now, fusion is very good. It is what's powering the sun. As we know, the sun is not very good at doing fusion, but it's so big that what it's doing is enough. It is effectively the only primordial source of energy and matter in the universe. Every other type of energy we know at some point started its career as fusion energy. Rays from the sun reach the earth, they are captured by plants, they go in the ground, they become oil or gas. So the gas that we burn at some point started as fusion energy in the sun. It has a lot of characteristics that are really, really nice. First of all, it is relatively clean, doesn't produce these awful emissions. is not very radioactive, it's only mildly radioactive, if at all. The fuel that we use, deuterium, at the first instance, is infinite practically. 1 in 6,000 parts in seawater is deuterium, so infinite supply. And importantly, something that I will emphasize again towards the end of my talk, very high energy density. So a kilogram of fusion fuel, whatever that is, if we had it fuse perfectly and completely, would produce the same amount of energy as roughly 10,000 tons of coal. So you fill this entire building pretty much with coal, roughly the amount of energy that you would get if you could burn perfectly a kilogram of hydrogen isotopes. Now, the UK as a whole is world leading in this domain. There is the #1 facility, as far as we know, is actually very close to where we are, in about 20 miles south from Oxford, in a site, in the Calum site. It's called the Joint European Torus, and I am using this to highlight one way to achieve this density, temperature, and confinement. It's called magnetic confinement, and the way this works is that you bottle, in inverted commas, the fuel in a very, very powerful magnetic field. Remember, the fuel, when it burns, can be 100 million degrees. 100 million degrees, you cannot put it in a bottle, you cannot put it in any material. You need to keep it somewhere away from everything else, but at the same time, you need to keep it together. Otherwise, you don't get the confinement, fusion stops happening. So the JET facility is actually using a very super sophisticated arrangement of magnets that creates a virtual force field only bottle that keeps the fuel, the burning plasma, away and safe. The picture here shows the inside of the torus, the inside of the jet, and this is a regular photography of one side of this when the fusion reaction is taking place. Produces this very nice purple color. This is not the only way to do fusion, however. This is another facility in the US, in the Lawrence Livermore lab, that's called the National Ignition Facility. Again, very expensive stuff, very substantial investment. The way NIF works is that you get a few hundred of the most powerful lasers there are pointing inwards in a perfectly synchronized and aligned fashion to a tiny fuel pellet, hydrogen pellet that sits inside this chamber that is manufactured with precision and accuracy that is unparalleled to anything else we are doing on Earth right now. The lasers blast, they create an inward pressure in this pellet of fuel that eventually leads to a fusion reaction. It is called the National Ignition Facility. Ignition stands for when you start burning the fuel, when you start burning hydrogen, you have enough fusion energy to push the rest of the hydrogen into burning. So it kind of ignites, the equivalent in chemical reactions. The National Ignition Facility does not achieve ignition, it achieves fusion, so you get thermonuclear neutrons, you get fusion reactions, but it cannot burn the rest of the fuel by itself, which implies for this facility that you have to put a lot more energy in than what you get out from the reaction. This concept of energy in, energy out is important in any engineering application. It's something we call gain, and I'll come back to that in a little while. Now, up until a few years ago, the scene as far as fusion was large, gigantic actually, government installations like the ones I just showed you. There is a plan to build another facility like that in the south of France, multinational effort from pretty much every country is in it, every big country is in it, including the UK, that's going to cost several tens of billions of pounds. All this knowledge that has been produced as far as fusion, however, that has been, for the most part in the public domain, has inspired and pushed a lot of people to think at a different scale and through of a different route. And in the last 10 years or so, an overwhelming array of small, medium, private companies have emerged looking at this same problem with the understanding that they may move faster, they may mobilize different types of resources, and they can try a lot more things than the traditional old mega installations are trying. A few of those companies have raised very substantial funds. The company that I am involved in, that we spun out of this department, this one is actually in this ballpark, and it's trying along everybody else for the same cause. So what is the technology, so to speak? In a one-liner, it is shock-induced cavity collapse. This means that you generate a shock and you make a cavity collapse like we saw the bubbles collapse in the bottle in the very successful experiment I ran a few minutes ago. So by cavity, I mean any void in a liquid, let's say medium, that carries your fuel, your deuterium, your tritium, your hydrogen. And we're going to call them bubbles from now on. And by shock, I mean something like this. Basically, a shock wave, is an area of very high pressure that moves into a domain where the pressure is just flat, normal, atmospheric. So it looks something like this. Very high pressure here, normal pressure here, and this travels and goes into space. I don't know why this stopped. It should have played many, many times. Let's see if we can get it to do something. Not really important, though. In this context, when I say high pressure, I mean pressures that are, let's say, 100 times higher than the pressure in the deepest, in the Mariana Trench in the Pacific Ocean, which is like 11 kilometers deep. The pressure at the bottom of that point, which is quite substantial, the pressures that we play in this case are 100 times higher than that, or a lot more, actually, as I'll show in a minute. So this video, when it was playing, was basically a schematic, a simulation, a computer simulation of the process. This is the real process now. And I have a few elements here that I want to highlight. So for practical purposes and for the design of this whole process, it is useful to separate two areas of activity. The first one is, how do I generate that shock wave, this very powerful shock wave? And the second one is, what is it that I am collapsing exactly? The first one I'm going to call the driver, and the second one I'm going to call the target. In this case, the target is this. It is the bubble in a liquid medium, the gas bubble in a liquid medium, and the driver for all our for our purposes is going to be the shock wave that is generated by the impact of this thing, which is just a piece of plastic or a piece of metal. I call that the projectile or the flyer plate. So what I do is I get something to fly towards the target, hits the target, you get the shock wave inside the domain before the bubble. This shock wave goes and hits the bubble. This is a very core concept of what we are discussing. Projectile goes at a certain velocity. This velocity is transformed by impact on the target into effectively a shock wave, this jump in pressure. This jump in pressure goes and does something interesting to the bubble. So driver and target. Let's talk about drivers first. An interesting way to drive this little projectile, this little thing that flies, is with the use of a gas gun, as it's called. A gas gun is nothing but a very long barrel. You get some compressed air maybe at the back. You increase the pressure a lot. Think of an air gun like a BB gun. The interesting thing is that the barrel can be very long. It can be 5, 10, 15, 20 meters long. And the pressure of the gas is a lot higher than a BB gun. So for this research that we've tried, we have employed first a single stage gun that achieves velocities of around 1,000 meters per second. Then we use the two-stage gun, which utilizes two different gases for practical reasons that can do velocities from 6 to 10,000 meters per second. 10,000 meters per second, for example, is very close to the escape velocity from the Earth. These are seriously high speeds. Okay, this is 10,000 meters per second is roughly 25,000 miles per hour. So the Top Gear guys would be really excited with this kind of velocity. This is one generation of one style, one flavor of drivers. It has limitations, so this range of velocities cannot be exceeded easily. Even the 10,000 meters per second, when you shoot the projectile at that velocity, you need to replace the barrel immediately because the barrel goes, so it's not very practical. So here's another approach that we are also pursuing, the electromagnetic launchers. This machine, which is now built and operating at First Light, is called M3 because it's the third machine that the company used or built for this kind of thing. And let me walk you around the geography a bit. These blue things are capacitors. These are seriously high capacity capacitors, and there are hundreds of them. They are organized in 6 banks all around, and they bring current through these plates into the center, into the test section. Something that I, not an electrical engineer, found astounding is actually that you have to use plates. These plates are the wires. You cannot transfer this amount of electricity through a single wire, no matter how thick it is, because it will melt immediately. So you have really gigantic, heavy plates that are actually transmitting the current. And what about the current? 14 million amps are stored in those capacitors at 100,000 volts, which is equivalent to 500 lightnings hitting at the same time, or equivalent to the power of the electric grid in the US and China put together, but for a very, very short time. So this electricity is discharged in 2 millionths of a second, extremely fast. This is a real challenge, by the way. It's not straightforward to close a switch at 14 million amps. But I won't go there. It's a different discussion. So what this does is that this whole current goes to a block that's about this big and creates, through Lorentz force, an outrageously high force on a small piece of metal. This tiny piece of metal that is sitting down there is pushed upwards by this force, accelerates upwards, and becomes the projectile, becomes the flyer plate, becomes what's going to hit the target to generate the shock wave. How fast does it accelerate? It accelerates at more than 1 million G. It goes from 0 to 45,000 miles an hour in a distance that's about this big. So again, Top Gear paradise. Theory says that this machine could do more than 20 kilometers per second, and the machine actually does very well. It has been commissioned and has been working for some time now. So it takes the whole discussion into a whole different domain. So this is the bit that you have to pay a lot of money for. You have to buy the capacitor, set up the machine. This is serious investment. There is another side to this coin, which is what do you do with the shock wave when it hits your target? So this is a typical target, or a target that I am at liberty to show you, maybe not a typical target. You can see it has 2 big bubbles here and a smaller bubble in the middle. And this video shows roughly the process again. Hit on the side, this is a bubble. at this version of this video, I don't know if you can see well on this side, there is a mirror that's sitting at 45 degrees at the back of this here, so we can see also from this direction. And what we see from this direction when the thing hits is a beautiful ring of very bright light. We first see a spot of light here, and then it becomes a ring of very bright light. This very bright light is plasma, is a generation of very high temperature material that happens because of the collapse of this gas in the bubble. So you may be wondering, why am I showing you this? What I said before, and this is really important, has to do with being able somehow to amplify the effect of this shock wave that, remember, I pay money for because it has to do with the installation, and get it to do more ideally than what it would do in the plain case, in the case simple shock wave, single bubble, etc. Can I get more? Can I get a more intense collapse? That's the question. I have to dedicate a slide into this because essential and fundamental and core into the psyche of this company, of the way things are done, is computer simulation. Computer simulation is an important field in science and engineering nowadays, but it's even more important when you're thinking about super fast, super small, super hot phenomena that are difficult to see, difficult to measure. Simulation offers you a way in. Caveats, of course, left, right, and center. You have to get it to work. You have to have the right kind of software. It has to be verified. It has to be confirmed. But once you are there, you can use it as a design tool to a certain extent. We're very proud of the work that has happened initially here and then at First Light regarding this, this technology. So let me walk you through this. The two big bubbles that you saw before and the tiny bubble in the middle, okay? The shock wave comes from the front, collapses these two bubbles, the big bubbles. The little one is shielded from the approach of the shock wave from the top. It doesn't know that something happened. Then secondary events of collapse in the two big bubbles, and this is the very bright red that you see over here, create some stronger shock waves that come and pinch this bubble in the middle. They create a different types of collapse for this bubble. Look at these shock waves, very red, and they hit this bubble in the middle and they create even redder red. That's a possibility. Quantitatively, what this means is that this is my shock wave, 1 gigapascal, and the maximum pressure that I'm recording in this domain is close to 40 gigapascals. So I'm having an amplification of about 40 in this case, as far as pressure. It translates differently to velocities, to temperatures, etc., but this is a good measure to show you something that it is indeed interesting. And it has to do with this fact. Note that the units I have here are gigapascals, billion of pascals. 1 gigapascal is 10,000 atmospheres. So 10,000 times 40, we are recording pressures of 400,000 atmospheres in this little world that's being impacted by the shock wave. It gets even more interesting if you let your imagination go wild a bit. So this is a kind of configuration that we can manufacture. It's not that easy, but you can build this. And it's basically an annular bubble. It's like a donut, a torus. And it has the little bubble sitting in its trough, in the crevice there. Similar collapse scenarios. Again, it blasts in a very similar way as the two bubbles that I showed you before, but in this case I was impacting this with an oblique shock wave, not perfectly aligned, just to check the sensitivity on that. And in this case, the recorded pressure, again within 1 gigapascal approaching shock wave that you basically cannot even see in this axis, goes to about 140 gigapascals, or in this case, 140 gigapascals, 1.4 million atmospheres. So a very, very high pressure and a fantastic amplification factor. I want to say a few things. Basically, these are the two technologies that we are pushing together. We are trying to get more and more and more powerful shock waves and better and better and better amplification. I want to say a few things about the chronology regarding how this work took place. I might have the first date wrong, but I think I'm not very wrong. This whole thing started with a discussion Professor Roy and I had the 7th floor of this building more than 10 years ago now. I think it was 2008, but it might have been 2006 actually. I don't know. And we discussed fusion at that point. The chap that I'm going to say more about later on, Nick Hawker, at that point was an undergraduate student, pretty much like you last year, who was doing a 4th-year project. And he approached me. I advertised this as a project. He approached me and said, can I do this? I said, sure. Then when he completed the project, he continued with a PhD on this very topic, working on shock-induced bubble collapse. At 2011, 4 of us, Nick Hawker, Stephen Brindle, who was then fund manager of Technicos, a fund very close to this department, Everett Gerchen, who was a program manager at ISIS Innovation, which was the tech transfer office name back then for Oxford, and myself went around, raised some funds, and incorporated the company. We created a company called Oxyntics. Here's another interesting anecdote. Oxyntics is, in my opinion, a brilliant connection of Oxford, the thing of Oxford, and the Greek word, ancient Greek word, syntaxis, which means fusion. It wasn't me that came up with this idea. It was actually Everett, a Dutchman. However, when Nick was picking up the phone as the only employee of the company at that point, saying, hi, this is Nick Hawker calling from Oxyntics, people were saying, what? From where? So it was obvious that something had to be done with the name, and we started calling the company First Light at that point. I think it was a very wise decision. For that period, the company pursued this iterative work of figuring out where things are using simulation and confirming that indeed what simulations are saying is correct, doing experiments. At 2015, the company moved to its current premises in north of Oxford, about 10 minutes north from here, in the industrial part. And during this period, it has grown from 1 to 40 plus people. And amazing in-house development, but also working very closely and all the time with the academic and all fusion community in the UK to advance this course, to advance this work. The plan for the company is demonstrate plasma, demonstrate fusion, demonstrate gain. And as I said, the computational models that have been developed lend very excellent confidence as far as this trajectory is concerned. And every time we get the facility to run the experiment for those conditions, for these conditions, and hopefully in the future these conditions, the confirmation of the computational results through experimental validation has been very encouraging. So we are very hopeful as far as this is concerned. What happens then, though? Okay, you get fusion. What do you do? This is not a disruptive technology. This is a technology that will make everybody's life a lot better, a lot cleaner, but you don't have to scrap everything we have and start from scratch. So the idea is that you can probably actually retrofit existing power plants, because the power generation side, the generators, the steam turbines, and everything else, which is the big bulky things that you see in power plants, remains intact. You don't need to change everything. What you need to plug in is the fusion reactor here and a heat exchanger that takes this red stuff, which is probably liquid lithium, a liquid metal that is used as a primary coolant and as a breeder for tritium, and just create the steam and everything you need from that point on. This is one possible manifestation for such a plant. You would use liquid curtains of liquid lithium, in order to capture all those neutrons and convert that kinetic energy into heat and take it forward. I will do something unusual now. I will say a few thanks at this point before I close, before I wrap up my presentation. There are a lot of people that have given me material for this presentation, or they have taught me interesting, valuable things, and I'm sure I am forgetting quite a few. I apologize for that preemptively. As I said, it started here in this building. Now it's in a facility in Yarnton, and the plan is that we're going to need a much bigger facility very soon. I have to say an extra word regarding Nick Hawker, who is currently the technical officer and CEO of the company. Nick, at some point, again, when he was about to start his PhD, I told him after he's done a brilliant work in his fourth-year project, hey, do you want to do a DPhil on this topic? He said, I want to do a DPhil, but it has to be on fusion. And his mentality, his thinking was, and still is, he wants to do this not because it's an easy problem, but because it's a very, very difficult problem indeed. And this kind of ethos, this kind of work approach permeates First Light today, which is great. Now, let's assume that you have fusion reactors, that you have gain. What's going to happen? Will anybody buy that electricity? This is, of course, an important question, especially for a commercial enterprise that, like First Light, that wants to sell at the end of the day. Someone can come back and say, you know, we're going to deploy an infinite amount of PV, photovoltaic cells. We're going to do offshore wind, you know, massively. You don't need anything else. We can cover. You don't need a base load kind of provision of electricity. So this is some data that have to do with global warming. You can take this any way you want. This is years down here, and this is each point is average temperature for various parts of the world. This is Europe, for example. This is the Americas. This is 1905, and this is 2015. Blue is cooler. Red is hotter. The national NOAA, the National Oceanic and Atmospheric Administration in the US that monitors this kind of stuff, just declared July 2019, 2 months ago, the hottest month ever in the history of the world. There is a spectrum of opinions, I want to say. There are some people that say that global warming doesn't exist, or that it does exist, but it's not humans that are responsible for this, that it is you know, solar activity or whatever. And there is another end of that spectrum that says that the recorded increase in temperature is 100% human activity. Opinions vary regarding where we are here. I want to believe, I think I understand that there are very, very few people numerically that are at 0% as far as their opinion. Some of those people are very influential, but there are very few of them numerically. So we are somewhere here. I don't know where we are. I think that the stakes are so high in this case that if we accept that we are not at 0, we need to pay a lot of attention. So there are some things that I believe we've already lost. It's not an easy discussion to have. This little thing here shows the ice cap in the Arctic Ocean, and you'll see how the thing evolves from the 80s till 2010. Again, this is remote sensing through a satellite and time-lapse photography, enhancing our perceptive capability. There are some things that we'll probably lose very soon. So Venice, bye-bye, I think. There is something I discovered just this year. This is a beautiful and amazing cave system very close to the place I come from. For the first time when I visited this year, I saw a sign outside saying the site is closed to visitors because the water level of the sea, which is linked to the water level inside the caves, is too high. And the guides there told us that the way things are going, that sign is going to be permanently outside this site. So that's really bad. That's why people are demonstrating. The UK is world leading as far as policies regarding reducing emissions and everything. However, the picture is not necessarily very, doesn't lend to optimism. And I've chosen one example from a really brilliant report that Systemic has produced, a company that specializes in this kind of analysis. This is the picture for India. So India it's a big country and it's getting bigger. This is the current profile of energy production. The black thing here is coal. Not very good quality coal, by the way, okay? This side is the projection, one of the projections regarding what's going to happen by 2040. So in this projection, the deployment of renewables has been maxed out. We are building and deploying PV and everything else as quickly and as aggressively as we can. And the need for energy has been kept moderate. So this is, in effect, like a best case scenario, because we are doing as brilliantly as we can in renewables, and we don't expect every single person in India to get an air conditioning unit in their house by 2040, which is always a possibility. Still, the gap is quite substantial. As I said before, the UK is brilliant in introducing policies regarding climate change and some very ambitious targets. It is a leading economy, it's a big economy, but as a country is not very big. If India goes this way, what the UK does doesn't matter very much. The amount of emissions that are going to be out there are going to overrun any gain that we get from this side of the world. So the question that I'm asking is, have we reached the point of no return? Starting roughly in 2013, I believe, people have started thinking that this is the case. This is an amazing event that took place here in Oxford that concluded that reducing emissions, what we are trying to do, cut down in the new stuff we put out there, may not be enough. Basically, people, even before 2013, but this has accelerated since, have started thinking that geoengineering, so big engineering projects to do something about CO2, greenhouse gases, and global warming at the planetary scale may be needed. This is not 2013, this is 2019. So this is an interesting paper, I think. It was published in Science Advances a few months ago. It involves the Western Atlantic ice sheet, which is disintegrating. When this thing melts completely and goes into the ocean, 3 meters of rise in sea level, Calcutta, Shanghai, New York, etc. This is not an meteorology paper. This is not a climate change paper. This is an engineering paper. What can we do about it? So the proposed solution here is to install snow guns, the ones you see in the slopes when you go skiing, in the Antarctic, bring seawater up where it's needed, convert it into snow, and try to restabilize this ice sheet. And the most conservative estimate regarding what's needed, if we could do it today, and that's not going to happen, it would be 12,000 super high-end wind turbines to generate like 150 gigawatts in order to bring the water up. This doesn't take into account losses, doesn't take into account the amount of desalination you might need, doesn't take into account a lot of things, the fact that you might not have persistent winds over there. So if this doesn't happen now and it happens in 10 years' time or 20 years' time, it might not be 12,000 wind turbines, it might be 50,000 wind turbines. I kind of think that this is not going to happen. My very last slide actually says that, in my opinion, fusion energy, apart from everything else, may have a huge role to play in projects like this, because you are not going to put 20,000 wind turbines in the Antarctic. You might, however, put 20 power plants that can generate this kind of power and actually start solving that side of the problem in a remedial fashion. It might be the only realistic alternative for our growing needs and for what we will need to do to reverse the damage we've already done. I'll thank you and stop here.